Hello friends, Namaste, welcome to this channel Dr.ARM's Chemistry. We are discussing organometallic compounds and today we are going to discuss the 18 electron rule. This is 18 electron rule. So this rule is having greatest importance while we are carrying out the study regarding the structure of the organometallic compounds. So this rule was formulated by Irving Langmuir in 1921. Irving Langmuir in 1921. In 1921. So this was formulated in order to view the extent of the octet theory of G.N. Lewis, which was based on the static atom model beyond argon in the periodic table. Means up to argon it was okay, but in order to study the complexes or compounds which are having the atomic numbers greater than argon, means those metals which are coming after the octet, means completion of the octet, that is having outer shell containing 18 electrons or more. So in that case, the rule formulated the equation. He derived the equation which is called Vc is equal to S minus E. Here this S here the Vc is the number of shared electrons. This is the number of shared electrons by the metal ion of a given atom in a compound. For example, if we are considering the organometallic compound, there is metal from transition series. So we are considering the number of shared electrons of a given atom like transition element. Now this S is indicating, means considers the capacity, that is the number of electrons required to complete the outer shell, that is valence shell. And this E, that is the number of valence electrons in the isolated atom. So this is our equation which was given by this Irving Langmuir. So if we consider any example, then we will understand it in better way. For example, if we take the NH3 molecule. We take this NH3 molecule. Then in this case, the Vc is equal to S minus E. So nitrogen has the electrons, number of shared electrons in the given atom. In this case, nitrogen has shared 3 electrons from its valence shell to produce 3 covalent bonds with 3 hydrogens. So it is Vc is equal to 3. Now this S, here this number of electrons required to complete the valence shell. In case of nitrogen, the valence shell is containing 8 electrons. Means the occupancy or capacity to accommodate valence shell of nitrogen is 8 minus E, the number of valence shell electrons in the isolated atom. If we take this nitrogen, then nitrogen has 3, means these 2 electrons in the pair state, and 3 electrons which are bound with hydrogens. So the number of valence shell electrons in the isolated atom has how many electrons? These 2, this one and this one. So 5 electrons. So 3 is equal to 8 minus 5. So in this way, we can calculate the other for complexes. Such as if we take the example of NiCO4. So this has, the nickel has the valence shell Vc. We show this Vc is equal to S minus E. So here Vc means electrons shared, number of electrons shared of the by the atom in the complex formation. So there are how many? 8 electrons. 8 electrons are shared here. So 8 is equal to the capacity to accommodate valence electrons is 18 minus the number of electrons, valence electrons in the isolated atom, that is, it is 10. So nickel has contributed 10 electrons in all. So these 10 electrons include the S subshell, that is 4s2 3d8, scandium, titanium, vanadium, chromium, manganese, iron, cobalt and nickel. So 8 electrons from 3d and 2 from 4s, so it makes 10. So 8 is equal to 18 minus 10. So in this way, we can calculate the same for chromium complex, CrCO6. Here the valence shell electrons, number of electrons shared by chromium, scandium, titanium, vanadium, chromium, these are 4 plus 2, that is 8 These are 12 electrons. 6 electrons of the given atom. So this has contributed 12 electrons is equal to 18. Here chromium has 18 capacity, 18 electrons, and there are 6 electrons actually contributed. The number of valence electrons in the isolated atom are 6. Scandium, titanium, vanadium, chromium 4 plus s electrons 2. So this is 4s2 3d4. So from this you will understand the use of this equation. So this is for the organometallic complexes in which the atom of our importance is transition metal. But in case of ordinary compounds in which the octet is containing, means outer shell is octet, then the octet rule was very simple. In this case, the S is equal to 8. That is the only difference. S is equal to 8 and rest of the things are same in the same way. But for next means if we consider the overall total transition block, that is D block in the mains, then this rule fits very well. Alternative electron counting procedures, now well known as effective atomic number, which is based on Bohr's atomic model, and electronic configuration was proposed by Neville Sidgwick. In 1923. This is also widely used rule, that is effective atomic number, EAN, shortly called EAN. So this rule was largely used by the 1960s. Because of its importance, it was most largely used during this up to 1960s. So the focus of this rule was not just the valence shell of electrons, but also on the counting of electrons of a compound. Means in that case, we are considering the atomic number, and overall the total should come to the nearest inert gas configuration. Means 8, 18, 32, like that. So this equation, or the very simple rule, that it gives, or it was used for explaining the stability of the compound or complex. If the effective atomic number of a given compound or complex comes out like equivalent to the effective atomic number, means nearest inert gas configuration, then the complex or compound is said to be very stable. But if it fails, means if it shows the nearest inert gas configuration and this effective atomic number having some difference, 1 or 2 or 3 electrons, then that compound is said to be unstable, means it is active. So inert gas configuration of the nearest inert gas element was considered in case of effective atomic number. This rule was popular, as we have seen, till 1960s, late 1960s. And it was applied to most of the all types of metal complexes. But afterwards, means by the 1960s, the chemical community said that instead of using the effective atomic number, it will be better to use the 18 electron rule. Why? Because the 18 electron rule is easy to apply. Means it is easy to apply, and that is why, and also it gives better understanding. So the EAN was then replaced by 18 electron rule. It is evident that the effective atomic number rule invokes the use of chemically active covalent electrons that result in the separate numerical stability standards. Means that we have already seen that 8 electron system means if we consider the transition metals and their complexes or compounds, we are considering the effective atomic number. If it comes closer to the 36, then it is the inert gas is krypton, and this is the first row of transition elements. First row. Similarly, if the element is from second row, then the effective atomic number is approaching to 54, and that is our inert gas xenon. That is second row transition elements. And if the effective atomic number comes out to be 86 or near that, the element is radon, and it is third row transition elements. 18 electron rule is found to be easily applied as a single numerical standard to the entire block of the transition elements. It is not restricted to either first row, second row, third row, but it covers the complete D block or transition metal elements. Then, because of this, it becomes popular for organometallic compounds also. To apply this rule, the assumptions made were ligands were considered as Levy's bases, and metal was considered as the Levy's acid. The 18 electron rule statement is like this: thermodynamically stable transition metal organometallic compound means the organometallic compound which contains transition metal are formed when the sum of the metal d electrons. How when they are formed? When the sum of the transition metal electrons means the metal d electrons and the electrons conventionally supplied by the ligands which are present surrounding the metal. So this equals 18, means the number of electrons from the valence shell of the metal, that is d orbital, means the capacity of d subshell is 10 plus 2 electrons from s subshell and 6 electrons from p subshell. So this total gives 18, means valence shell of the metal contains 18 electrons. Means total capacity to occupy the electrons is 18. And we have to consider other value, which is the actual valence electrons present in the metal, which are contributed here during the formation of the complex. And we are also, if we equate this, it gives 18. So this is very simple. Means if the complex is stable, the sum of these electrons comes out to be 18. But the complex is unstable, the sum of these electrons will be less. It may be 17, 16, like that. and depending upon the 18 electron rules, means the counting of electrons, it is better or it is suitable to predict the stability of the complex as well as structure of the complex. Means the number of metal bonds, number of electrons contributed by that, and number of bonds present for the given atom, metal atom. Means how many metal bonds are attached to the metal. So we will see with the example. Alternatively, when the metal in the question is or achieves an outer shell configuration of Ns2, N-1D, and P6, there will be 18 electrons. So that is we have seen. So if the Ns2, N-2, 1D, 10, and P6. So this gives 2 plus 10 plus 6 gives 18 electrons. Means in overall, every metal atom present in the complex will have the total count, maximum count will be of 18 electrons. If it is less, then it will represent the number of metal bonds. So that will help us to formulate or understand the structure of the complex. There will be 18 electrons in the valence shell or vitals, and closed stable configuration is attained. These conditions are favorable when the metal electron is reaching electrons. Means in order to give the stable structure, the metal atom should be in low oxidation state, means or zero oxidation state, so that the complex is stable. And ligands should be in higher good electron acceptor, means ligands are good pi acceptors. Metal should be good sigma donor. The stability of the complex is predicted, the same thing I have discussed here, by considering the electrons contributed, means the total count of electrons. It is also predicted that the possibility of metal bonds, that is also discussed, I have told you. Now there are two types of methods for counting the electrons. There are two methods for counting electrons: the neutral atom method and oxidation state method. There are two methods of counting electrons. Electron count by two methods. One is neutral atom method. So we can shortly call it as NAM. And second is oxidation state method. It can be shortly called OSM, oxidation state method. So both methods are useful, but means they are having their own importance or own ease of counting electrons. The first method, that is neutral atom method, is more foolproof, and it does not require the correct assignment of metal oxidation state. Means without the requirement of the oxidation state, it can count the number of electrons, whereas the oxidation state method is more realistic, as it reflects the precise number of electrons available for donation on a ligand. Now we can understand this by considering the examples. If we take the example of like this, PPH3 PPH3 plus 1. So in this complex, this allele has 3 electrons, 3 carbons, 3 electrons. Now, according to NAM and according to OSM, the electron count is like this. This Ru contributes 8 electrons. Then this eta 3, 1, 2, 3. So this is allele, eta 3 allele. Allele contributes 4 electrons. Then the 2 phenyl triphenyl phosphanes, 2 PPH3s contribute 4 electrons. This carbon monoxide CO contributes 2 electrons. Then oxidation state plus 1, that is we say charge, is counting as -1. When there is +1, the charge is -1 is deducted. So if we make the total 8 plus 4 plus 4 plus 2 and -1 gives 12 plus 4, that is 16. And this 2 minus 1 means 1, that is 70. 6 total is 70. So here eta 3 is contributing 3 electrons, means alone, and Ru contributes 8. So it gives 3, 15 and 16. Total is 16. So this charge is deducted from the count. Now if we use OA oxidation state method, the Ru is in 2 plus state. So the electrons contributed by the gallium are 6. Here Ru is in 2 plus state. Then alkyl groups are contributing 4 electrons because we are considering oxidation state method. Then 2 phenyl groups are contributing 4. This carbon monoxide 2, and there is no need to count the charge, not required. So the count is 16. So in both ways the count is same. Now when we want to count the number of metal bonds in a complex, so calculating bonds, metal bonds. There are it gives the method. So first of all, it is necessary to determine the total valence electrons in the entire molecule. So determine the total valence electrons in the entire molecule. So this is first. So this can be done by using this simple formula, that is number of valence electrons plus number of electrons from each ligand. Number of electrons from each ligand. Each ligand plus charge. So this is called A. So this total valence electrons are called, this is represented as A. Now second rule of this step is subtract this subtract this subtract A from 18 into N. Here N is equal to number of metal atoms in the complex. Number of metal atoms in the given complex. So this can be given as 18 into N minus A. Like this. And this is say B. Value comes out to be is called B. Now the third step. So it has a divide B by 2. B is to be divided by, means this value, whatever it comes is to be divided by 2 to get total number of metal bonds in the complex. And in the same, if we get what is A is divided by 2, it gives the number of electrons, per atom of metal, electrons per metal atom. So we can obtain this various information by following these 3 steps, that is 1, 2 and 3. So here the important figures are A, this B, and this formula, this is N is equal to number of metals, this formula. So we have to remember these things here while calculating the metal bonds present in the given complex. So we will see with some examples. Now, after calculating or taking these 3 steps and obtain the values, from these values we understand. What we understand? We can understand if the number of electrons are 18. If the number of electrons are 18, there is no metal bond. Means when this B upon B is divided by 2 and this B is divided by 2, when this A is divided by number of metal atoms, and if it gets the value 18 electrons. So this shows that there is no metal bond. There is no metal. If this value is 17, then there is one metal bond. If it is 16, there are two metal bonds. If it is 15, then there are three metal bonds. So in this way, we can have the various information, so which will help us to formulate, design the structure of compounds. Now we will understand this with using some examples. See how to calculate the total valence electrons. For example, if we take this complex CrCO6, then formal oxidation state of the metal is considered, here it is 0, and total valence electrons are calculated here as, so the chromium contributes how many electrons? 6, because in this series the chromium has 6 electrons, scandium, titanium, vanadium, chromium 4, and S electrons, means there are 4 electrons in the D subshell and 2 in the S subshell. So it makes 6 electrons of chromium, plus there are 6 carbon monoxides. So 6 into 2 means each carbon monoxide shares or donates 2 electrons. So 6 into 2 gives how much? Total is 18. So 6 into 2 means 12 plus 6 is 18. So in this way, if we take the example of FeCO5, this is having also formal oxidation state 0. So the number of electrons contributed are scandium, titanium, vanadium, chromium, manganese, iron. 6 electrons from D subshell and 2 from S. So totally it gives 8, plus 5CO, 5 into 2, that is 10, plus 8 is 18. Then if we take another example, eta 5. So this is eta 5. Cp, cyclopentane, FeCO2, Cl. So here the Fe is, this complex has +2 formal oxidation state, and the electrons contributed are like this. The eta 5 contributes, the Cp contributes 5 electrons and 1 from this Fe. So it gives total 6 electrons are contributed by Fe. 1 electron means there is +2 oxidation state. So only 6 electrons are contributed by Fe. This 6 is contributed by Cp. There are 5 Cp. So 6 plus 2 plus 2 means 2 carbon monoxides contribute each 2 electrons. So plus 4. and plus 2 electrons by the Cl. So the total is 6 plus 6 plus this 4 plus 2 means 18. So in this way total valence electrons are calculated. So we are having also more examples. If we take another example, that is CH3 MnCO5, then it has plus 1 oxidation state, thermal oxidation state. So the contribution is like this. So this methyl group contributes 2 electrons plus Mn contributes 6 electrons plus carbon monoxides contribute 5 into 2, that is 10. So total is 18. Now another example is FeCO4 2 minus. So here the oxidation state is minus 2, thermal oxidation state. Then Fe contributes 8 electrons plus these carbon monoxides are 4. So 4 into 2 or 2 into 4, that is 8, plus the charge plus the charge minus 2. When there is oxidation state thermal minus 2, we have to add 2 electrons. If it is plus 1, we have to reduce minus 1. If it is there, so we have to carry out these calculations in this. So we will see some more examples. It depends upon the thermal charge. So we will take this example FeCO4. So here 2. So total is 8 plus 2 means 80. Now another example, beta 5 Cp2 CO plus means oxidation state is here plus 3. Oxidation state is plus 3. So here the thermal charge is plus 1. So here total count is 6 into 2, eta Cp. Here are 2 eta Cp's. 1 eta Cp gives 6 electrons. So 6 into 2 plus cobalt has 7 electrons, and for charge there is minus 1 and it gives 18. This way if we take another example, MnCO6 plus 1, so it has plus 1 charge, thermal charge. The count of electrons is for Mn 7 electrons plus 6 carbon monoxides into 2, 60 into 2, and for this plus 1 there is minus 1. We have to remove 1 electron. So it is in this way. There are a variety of examples that gives the total valence electron. Remaining contents we will see in the next lecture. So please subscribe to this channel and also press the like button. Thank you very much for watching.